Hi guys, welcome to this page of the notes, and I'm really excited about taking a look at this particular problem with you. I mentioned at the beginning of this set of notes that one of the things we're going to do in this chapter is use exponential and logarithmic functions to model naturally occurring phenomenon. Exponential and logarithmic functions work really well for this type of mathematical modeling. And I kind of described that for you here. We're going to use this exponential growth model to do things, to describe things like population growth in anthropology, bacteria cultures in biology, and even compounding interest in economics. And that's just to name a few applications that exponential functions have when it comes to modeling natural phenomenon. In this case, we're actually going to use the exponential function to work on this problem, which does deal with population. It actually has to do with the attendance at for a particular basketball team. Now, before we take a look at the problem, I want to talk about the equation real quick. And there's actually one other way that you may see this equation written. It means the exact same thing. The notation will just be slightly different. You might see it like this. Capital A is equal to A naught times the quantity 1 plus R raised to the t power. The only difference here is instead of using AT and a lowercase a, we'll use capital A and A naught. And I'll talk about what both of those mean right now. So let's talk about what all these variables mean. Well, first of all, lowercase a or A naught. A or A naught. What those are going to mean is they're going to represent the initial amount or the starting amount. Okay. Whether you call it A0 or A naught, it just simply means A initial, the initial amount. How much are you starting with? Most of the time, I prefer to use A naught. So if you're taking this class with me on quizzes and tests and things like that, I'll almost always use A naught as opposed to lowercase a, just for consistency in my class. If you're taking this course somewhere else, it depends on what your teacher likes better. As far as AT or capital A, in either case, whichever form of the exponential growth model your particular teacher uses, it's going to represent the final amount. It'll almost always be what you're solving for. The final amount, all right? AT or A. Let's keep going. R. R is going to be the rate. And a quick thing about the rate, and you'll need to remember this, something that you'll have to do to the rate. I will almost always, in fact, your book, even on quizzes and tests, we will almost always give you the rate as a percentage, which we've done here in this problem. But a percentage will not work in the formula. It doesn't work. You must convert the rate to a decimal. Which is very easy to do, right? To convert a percentage to a decimal, you just simply divide by 100. Or take the decimal point, move it 2 spots to the left, all right? Really easy, but you've got to remember to do it, all right? If you just plug 5 into the formula, you're not going to get the right answer. But on my multiple choice test, I guarantee you that I'll take 5, I'll plug it in, and whatever number you get, that will be one of the answer choices. I will be checking to make sure that you remember this. You got to convert the rate to a decimal, all right? And then the last one is T, and T is really easy, as it almost always does. T just represents the time. And of course, depending on the problem, will determine what the time is. Is it seconds, minutes, hours, days, weeks, months, years? What the time is depends on the problem. So now that we know what all of the variables mean, let's go ahead and take a look at the example problem that I have for you. We'll see if we can't work it out. Here's what we've got. We have the attendance for a basketball team increases at a rate of 5% per game during a winning season, right? Which totally makes sense. As long as the team is winning, everybody jumps on the bandwagon and wants to go to the game. So you can see why the attendance would increase as long as they're winning. What I want you to do is find the number of people in attendance during their 15th home game if the season opener had 23,500 people in attendance. All right, here we go. Let's do a little bit of highlighting real quick. First of all, really easy to spot, rate of 5%. So we now know what R is. I'll have to convert it to a decimal, but we'll worry about that in a second. Next, we know the season opener had 23,500 people in attendance. That's the initial amount, right? How many people were present at the start? 23,500 people were at the first game. So that's going to be A naught. Sorry, that's my highlighter. Right? That's my initial amount. How many people at the first game? What I want you to do is figure out how many people are going to be in attendance. What is that final amount? How many people? But I want you to find it at their 15th home game. So we're going from the first home game, which had the initial amount, to the 15th home game, which has the final amount that I'm looking for. What that means is that 15 is your time. We'll plug a 15 in for T. So in this case, time isn't even measured in minutes or seconds, weeks or months. We're actually measuring time in games. Which game is it? Well, it's the 15th game. All right, here we go. We're going to go ahead and take our equation, which I'll just rewrite for you right down here. A is equal to A naught 1 plus R raised to the T power. Let's go ahead and plug in what we know. We know that we're solving for A. I know that my initial amount was 23,500 people. Actually, let me rewrite that so it's a little clearer. $23,500 people. I'm going to have 1 plus. I need to convert my rate, which is 5%, to a decimal. Move the decimal point 2 spots to the left, or use your calculator and divide by 100. You'll get 0.05 as a decimal. And then my T is 15. It's the 15th home game. All right. What you want to do, of course, is you'll use your calculator to do this. It's a plug and chug problem. Just don't fat finger something on your calculator and make sure that you do the order of operations correctly. 1 plus 0.5 would be 1.05. Raise it to the 15th power, then multiply that by 23,500, and what you should get is 48,855 people. So for this particular basketball team, during a winning season, at their 15th home game, we're going to estimate there'll be about 48,855 people in attendance, or roughly 49,000 people, which not bad. That's pretty good attendance, especially during a winning season. That's awesome. So anyway, what you hopefully can see here is that we can use these exponential functions. And again, the reason it's an exponential growth model is because I have a variable in the exponent position, right? T is a variable, and it's in the exponential position. It's an exponential growth model because we have an increasing, in this case, population or increasing attendance. And so we have exponential growth. We'll get a lot more work with this in section 8 of this chapter. You will see this formula again in section 8 of this chapter, where we do not only more problems like this, but even problems that are a little bit more complicated than this. We can do some awesome stuff with exponential functions. Guys, head on over to the next page of the notes, and we'll take a look at exponential decay functions. What happens when the base is less than 1, right? When the base is a fraction or a decimal, and we'll see how we graph those along with transformations. So head on over to the next page of the notes. I'll meet you guys there.